Okay, so we want to talk about continuity, which between that and infinite limits is going to be the last thing that we look at. So the most important thing is going to be discontinuity in this section. So we want to take a look at these three types of graphs here where we're going to see discontinuities. So the first one, all the way to the left, if we see a graph that has a hole in it, and so the function is just going to be undefined at C. So we'll trace this and notice that there's just that hole, but there's no defining point at C. So we know f of C is undefined. That means that we're going to have a discontinuity. The next one, the limit from the left is not equal to the limit from the right. We'll define that in a few minutes, but that means that we have a discontinuity. And then lastly, the function as a whole, but it is defined right below it there. So that means that f of C is defined, but the limit's different than f of C. So those are going to be the three scenarios that we want to look out for discontinuities. So let's define. A function f is continuous at C, at x equals C, if the following conditions hold. And it's going to be based off of those three graphs that we have there. So we're basically going to do the opposite of those three graphs. So first, f of C is defined. So that means we can plug in x equals C and we'll get some number. It's not just going to be undefined. Secondly, the limit as x approaches C exists. And then third, those two first things are going to be equal. So the limit of f of x is equal to f of C. So a definition, we say f is continuous on AB, the interval AB, if it's continuous at every single x value inside that interval. So easy enough. So let's look at an example. We want to discuss the continuity, and whenever we do this, we want to basically list the discontinuities if we can, and talk about where it's going to be continuous. So we're given f is equal to 2 over 3 minus x. So we can see very obviously that we can't plug in 3. If we do, we're going to have a vertical asymptote, which is a discontinuity. We can't really get rid of it. So if we looked at the graph of that thing, we'd see we can plug in any value at all, but x equals 3 doesn't work. So f is going to be continuous everywhere except x is equal to 3. And we can write that in interval notation if we want. Negative infinity to 3, union 3 to infinity. So that just has a whole of 3. So the next one is pretty similar. We have x minus 3 divided by x squared plus x minus 12. And right away, if we don't know what's going on with this thing, we can see the denominator is a polynomial, and so we want to try to factor it. So let's do that. And so we have x plus 4, x minus 3 on the bottom. And so technically we can cancel that. It's going to become a different function though. But we know we can't plug in 3, we can't plug in negative 4. And so those are going to be the discontinuities that we have. Okay, so the strange thing here is that x equals negative 4 is going to be a vertical asymptote, but x equals 3 is going to be a hole in the graph. And remember that we basically canceled that x equals 3. So we're not able to cancel negative 4. We can cancel 3. And so the difference between those is x equals 3 is what we call a removable discontinuity. We're able to cancel it and basically plug the hole. Negative 4 is non-removable. It's just a vertical asymptote, a jump in the graph. In this case, a vertical asymptote. And there's just no possible way to cancel that. Alright, lastly, for the normal functions, we'll take a look at p of x is equal to 3x cubed minus 2x squared plus 11x minus 3. And this is a polynomial, so it's continuous everywhere. All polynomials are going to be continuous everywhere. And all rational functions are going to be continuous everywhere they're defined. Alright, so let's look at a piecewise function. Here k of x is going to be 2x plus 1 if x is less than 2, and x squared if x is greater than or equal to 2. So the best way to go about this, just to start, is maybe to graph both of these functions on the same plane. And if we do that, it's going to look like this yellow graph that we come up with down here. And so remember that a piecewise function is very clearly defined. We see 2x plus 1, but that's only going to be to the left of 2. And x squared is only going to be to the right of 2 and including 2. And that's why this graph looks so strange. So if we plug in 2 for the first and second function, we're going to see there's that little jump in the graph there. So 2x plus 1 would give us 5 if we plugged in 2. And since it's strictly less than 2, we're going to have a hole in the graph there. X squared, if x is greater than or equal to 2, that's going to be a closed dot. Alright, so we can see that since they're both polynomials, the only issue we might have is actually at x equals 2, and that's what's happening here. There's a jump. If it was 2x instead of 2x plus 1, this thing would be fine. It would be continuous everywhere. But that 2x plus 1 ruins it, shifts it up. Alright, so this notation here, the limit as x approaches c from the left is the limit from the left. The limit as x approaches c with the plus sign there is the limit from the right. So that means we're coming in from the right of whatever the c value is. So we say the limit exists if and only if those two things are going to be equal. So let's look at this example. Here we all know what function it is. We're just going to call it some function f. So whatever f is here, we can see that it's approaching 4 from the left and the right. And for both of those, it's at a height of 3. So we can say the limit as x approaches 4 from the left is 3, and from the right is 3. And so that means that the limit itself is 3. But if we see the step function here, the limit as x approaches 1 from the left is negative 1, but from the right it's positive 1, and so we can't say that the limit exists. Alright, so here we have a theorem. F is continuous on the closed interval AB if it is continuous on open AB, and the limit as x approaches A from the right, from the inside, is equal to f of A, and the limit as x approaches B from the left is equal to f of B. So we're going to look at the semicircle y is equal to 9 minus x squared, and we want to show it's continuous on negative 3 to 3, closed interval. So we know right away that it's going to be continuous on the open interval. We can plug in anything we want, it's always going to be defined. And so now we just need to check those other two conditions. So we want to check that the limit as x approaches negative 3 from the right is equal to f of negative 3. And they're both equal to 0, so it's going to check out. Now we do the same thing with 3. So the limit as x approaches 3 from the left on the inside of the interval. And we want to see if that's going to be equal to f of 3. And so it is. Alright, infinite limits. So we want to look at the function f of x equals 1 over x minus 2. So we can see very clearly we have a vertical asymptote at x equals 2. Can't plug that in. And so if we take the limit as x approaches 2 from the left, we go to negative infinity. From the right, we go to positive infinity. And we want to see if we can do that algebraically. And it gets a little bit weird here when we try to do this. So if we do a limit the same exact way that we've done them previously, meaning we're going to plug in that c value to whatever function we have. In the first one, we're going to have 1 over 2 from the left minus 2. So that's a number just smaller than 2 minus 2, which is negative. So we have 1 over 0 from the left, we'll call it, a really small negative number, which is going to blow up to negative infinity. And if we do the same thing from the right, 1 over 2 from the right minus 2, that's 1 over a really small positive number, which is going to blow up to positive infinity. Same thing for g of x here. If we want to find the limit as x approaches 2, from the right, we're going to have 5 minus 6, that's negative 1, divided by 0 from the right. That's going to be negative infinity. Even though I wrote positive infinity, that should be a negative infinity because we have 5 minus 6 on top. And from the left, 5 minus 6 is negative, but we have a negative on the bottom. And so it's a double negative, and so those should be switched there.